Yes?
Percent or point?
Points. That's why I stalled for a little bit before I answered, because I automatically translate to percentage, and I realized, no, you want raw points, so I put that out there. I know, it's easier to multiply than divide, I got it. Other questions?
Are we getting it back on Wednesday?
Are you getting the exams back on Wednesday? No, we're getting them back tonight.
Tonight?
Yeah.
Are we gonna go over it tonight, or? if they're-
Overtime?
Are we gonna go over it tonight? Like
Yes.
last
Oh,
time?
yeah, of course, when I hand them out, I also
Okay.
go over the exams too. So we'll stop a little bit early, so we can do that just like we did for exam one.
Yeah. Okay.
Other questions? All right, we'll get started on the new stuff then, right? Because you're all excited about the new stuff. Because assignment 3 is going to be about the new stuff.
Yeah.
And we are here. Right, that's what I was going to point out. You know, we're down to here, Danny. Right? We only have 2 chapters left, 1 assignment, 1 exam left, 2/3 the way through. Here we go, 2 chapters, 2 weeks. Another way to put it? All right, back to you. You. And you. Okay, so now we're going to talk in detail about input and output subsystem. Okay? In order for us to best understand the complexities that we're dealing with the input-output system, I started to say I/O. I will use I/O most frequently, so just go ahead and do the translation. We need to understand the different categories of I/O so we understand what our requirements are, right? Because that's going to drive our designs, our algorithms, our implementations. All that stuff is going to be driven by what is it we're trying to push stuff through, into, or back from, right? So these major categories of things like human-readable devices, obviously things like your printers, your scanners, your all-in-one devices now, your video terminals, your keyboards, all those kinds of things are human-readable devices, right? So that category has some special connotations because it's going to drive some input-output requirements that are different from, say, machine-readable devices, such as your mass storage devices, your external storage devices, where you're trying to just ram whole pages of bytes through in a single transfer because it doesn't have to interpret the stuff, whereas in human readable, the I/O device has to interpret the stuff so they can make it human readable or translate it from human readable to something the machine can process. Whereas machine readable stuff, it's just a whole bunch of bytes. Here you go, right? So here's some other examples of some machine readable devices. Then of course there's communications, input-output things. Of course, USB is well known, FireWire is pretty well known. Your network card, your NIC, right? That's also a communications input-output device. And there's some others as well. So there's some specialized I/O devices that you might not be familiar with now, but you might get jobs where that's what you're doing. You're just pumping stuff through these specialized I/O devices for a very specific purpose. And sometimes it's because you're working with things like sensors or actuators and stuff like that. Then of course, modems, there's a lot of different kinds of modems. And over your careers, I expect there'd be a lot of different kinds of modems too. Some we haven't even thought of yet. Maybe some of you are already thinking about, but it hasn't been implemented yet, and that's what you're gonna do. All right? So the other way that we need to take a look at our I/O devices, and again, to help us understand the requirements, is to take a look at their performance, right? Because obviously a keyboard, and I don't think my data rate's quite that fast, but some nominal value for a keyboard could be 10 bytes per second. All the way up to things like a bus, which is transferring 520, notionally 528 megabytes a second, And of course, now we've got some really, really fast buses in our HPC devices that are, basically the speed of light. And that's kind of fast, okay? So that your I/O system is going to have to scale these ranges of data transfer rates, what we call data transfer rates, right? That's a pretty big difference. And it's going to drive the whole way that we drive bytes through, either into or out from the computer, from the systems. Sounds easy, right? Non-committals, bunch of non-committals, all right. All right, so some other ways we can state this is going back to that last slide, talk about the data rate. Okay, specifically when we talk about the data rate, orders of magnitude of difference is the thing that's really driving it. We can have some devices which are a little bit faster, a little bit slower, some that are worried about single bytes coming through versus whole blocks coming through. That's a bigger issue, okay, than individual or minor little differences between transfer rates. And then there's our application, right? The whole reason why we're pushing bytes into or out from our computing system is because, well, there's data out there that our application wants to work with. It's either going to generate, process, or create data that's moving through the I/O subsystem. Okay, so that means, of course, our disk system has to have a file system, which we talked about in the last chapter. The disk system is going to have to have a virtual memory paging system. We talked about that a little bit, but we want to talk about it in some more detail because there's some things that we can do with our virtual memory system when we look at it from an I/O perspective, right? And then likewise, terminal or higher applications need to be able to access the data, either to move it in or transfer it out, move it in, manipulate it, transfer it out, just like we talked about. Then we look at what the data itself means. What format is the data going to be in when we actually do the transfer? Goes back to the discussion we just had, right, about is it machine readable or is it not machine readable? Because if it's machine readable, I'm going to be worried about things like encoding schemes, and I'm going to have to do that on the fly in some cases with my data as I'm preparing it to move in, or as I'm processing it after I've received it. Okay, I may have to do that. Back to the instant transfers, we're going to take a look at the differences between sizes of our block transfers, because that's what we're really talking about with unit of transfer, because the streaming stuff, the stuff that comes in one character at a time from your keyboard, for example, you don't really have much control over that, as we're going to see in some of our later slides. So the unit of transfer, not so much a big deal for what we call streaming I/O, but for block I/O, like transferring to our long-term storage devices, that's going to matter. Is it a 512 byte? Is it a 24 byte? Is it a 768 byte? Block, whatever we use, we're going to take a look at some issues with that, because that's going to drive the efficiency of our I/O subsystem. And finally, error conditions. And we'll take a look at this too from the hardware perspective, as well as what we could do at a systems level with error detection. We're always going to be concerned with error detection because when we're moving things between two different systems, stuff happens, right? Have you ever accidentally pulled out a cable that was connecting your USB drive from your machine? Yeah? Did your system recover? Yeah. Because we're looking for error conditions and we're processing them. And not all I/O devices have the same kind of error handling built into it. So the error signals, right? It doesn't have the same error signaling mechanisms built into them. So we're going to have to deal with that, and we want to work with it so we can let our OS survive ourselves. Another way we're going to divide up our I/O is by the different techniques. And we started touching on this just a little bit in a previous chapter. We're going to go into great detail here, okay? And these are the three things: programmed I/O, interrupt-driven I/O, and direct memory access. Remember I said in the last chapter that in order for us to implement a paged memory management system, we need a specific piece of hardware, which was called a
Memory
main
management.
memory unit. Main memory unit. Really?
Or
Memory management.
memory management unit, yeah.
For what? Page, you said PMM?
Paged memory
Oh,
management,
PMU.
right?
Crap.
So like the virtual memory system where we require the PMMU, in I/O subsystem, we're gonna look at what happens if you have one of these DMA controllers, DMA, direct memory address controllers. Now, I'm not telling you you have to have one of these because we still do programmed I/O and interrupt-driven I/O today. And a lot of systems will also provide this DMA controller, which allows us to do DMA programming. But in subsystems today, we're using multiple techniques. We're not necessarily using just one technique above all others. There are times when other ones come into play. Okay, so what's programmed I/O? Basically, the processor is busy waiting for all the I/O activity. And if that's the job of that particular program that you're building, is to get data out of a sensor, that's all it needs to do. Sit there and wait for data from a sensor. It gets data from a sensor, it then processes, according to the programmed instructions, that I/O operation, and then it goes back and waits for more I/O. Interrupt-driven I/O, however, is where we're going to use interrupts. Okay, programmed I/O, we're waiting for the data. Could it be initiated by an interrupt? Yes, that might be how we're notified. But in the case of interrupt-driven I/O, what we're going to do is we're going to use interrupts to determine when we go look for data. Whole different process, okay? So what happens in interrupt-driven I/O is the processor is going to initiate an interrupt when it wants to be notified of some I/O activity. When that I/O activity happens, it then goes and erases it being the device that received the data, raises an interrupt, processor goes over and processes that data that was just made available, and then returns to what it was doing. We're going to look at these in more detail. This is just a general description. In DMA controller, or in DMA techniques, you'll have this DMA controller, which is basically a mini CPU. It's a less capable CPU. So for all of those of you who are saying, you know, when they make CPUs, right, they make these batches of thousands or hundreds of thousands at a time, right? And then the next great, wonderful CPU comes around, and you've got these cases and cases of these old CPUs that you can no longer sell because everybody wants the new ones. Everyone wants the one that goes 500 megahertz faster. Everyone wants the one that has another L2 cache built into it. They want the best one. They don't want this one that is sold last year. When you went buying for yours, did you look for the one that was sold last year? Or did you look for one that is the best?
But that's
Thank you. Last year, I'm on a budget. Got it. There is still a market for that. But you're not looking for one that was sold 4 years ago. Okay, so that's what they were looking at. So we're just looking at this market of these old CPUs saying, can I find a purpose for them? And some student who's buying last year's because they can't afford the latest and greatest says, hey, let's take this old CPU here, throw it in here, make a PROM just for this thing, and it's a DMA controller. Worked. Got their thesis, got their doctorate, got a job at the first company that was marketing this thing, doing pretty good. Okay, so yeah, think like that. That's good stuff. So the idea being, you take this old processor, this old technology, and you build your own firmware for it to do some very specialized task. In this case here, its job, the whole job of this little mini old CPU here is to do all the I/O activity. So the famous, rich and famous new CPU that is the main CPU of the machine can go off and do CPU stuff. Okay? That's kind of the idea behind DMA controllers, DMA processing. Only make the main processor work when it needs to do things like start the I/O and whatever it is it's supposed to do once the I/O is completed. Let this DMA controller do everything else. All right, so that's what we're going to do. So now let's go take a detailed look at those three techniques that we just introduced to you. Okay, starting off with programmed I/O. So the idea with programmed I/O is that the CPU is going to do all of the I/O activity. When I say do all the I/O activity, literally, it's creating data. In this case here, you're up here in the user space, right? And you said, oh, I've got this string of 8 characters here that I decided I wanted to send out to output device ABC, whatever it happens to be, okay? So it creates the string that it wants to print. Then it has to somehow move that data from user space to kernel space because we're going to do an I/O action, which means we're going to talk to an I/O channel, an I/O processor, excuse me. We're going to talk to an I/O processor. The I/O processor will only listen to the CPU when it's in kernel mode. Okay? It's not going to let just any user mode process talk to it because this is protected stuff. This is system stuff. It's protected. So it needs to be in kernel space. So we need to copy the string from user space to kernel space. And then while we're in kernel mode, we can then, our process can then move 1 byte to that output device, go to the next byte, output device, and so on. All right? I was still overly simplifying. Because depending upon the output device, in this example here, we're actually talking to a character-oriented or stream-oriented I/O device, right? Remember earlier I said 2 different types of devices, string-oriented and block-oriented. In this example here, this is an example of string-oriented or streaming. Sometimes we refer to this as streaming, which is the more generic word. Because what we're doing is we're literally streaming these bytes out 1 byte at a time in the order that the bytes need to be maintained in. So I will always transfer them in this order here, first byte, second byte, third byte, and so on, 1 at a time, okay, for string-oriented or streaming output. In block-oriented, that's where we're going to generate a whole page of data, fill it in with whatever bytes we want it to be, and then we transfer that whole page at a single time, a single transfer. Okay, that's block-oriented. So in programmed I/O, it's a lot easier to see it in streaming or stream-oriented because that's essentially when you would really use this particular technique. It's how we first started doing I/O, and it still works today for some serial devices. Okay, so what's going to happen in a streaming I/O is the first thing that has to happen is this process has to see if it can talk to that particular device. Meaning, is this device connected, powered up, and electrically talking correctly on that particular protocol, whatever it happens to be, USB, whatever. Okay, so it has to do all that. Now, most I/O, this is kind of review now, right? This is all stuff you had in your computer architecture class, right? Where you actually had to send a word to the I/O device, which basically says, I want you, and the device comes back and responds saying, okay, you requested me, I'm available, I'm yours, and I'm in good status, and then you know you can process. Otherwise, you're still waiting for the return of that signal, that word, right? So you're waiting for a status word. So that's actually happening between all these steps, right? First, it has to get that device. Are you available? I intend to take you. And then it comes back with a word saying, ready. Once it's ready, then you can go with the next word, which is a byte transfer. Then another byte transfer, and another byte transfer until you're done with the device, and then you send out a word that says, I'm done with you, right? Remember that stuff?
You get for that.
Really?
1 through 7. I think Tal focused more on like the theory and like actually like creating circuits and
Yeah,
stuff.
yeah, we're gonna get into that too, but they're still supposed to do this. Okay, I will be working on that. Okay, so in pseudocode, what does that look like? Well, you're getting copy from user, gonna pass it a pointer to the buffer, you're gonna have a count, right? And then all you're just gonna do is go from 0 to count, transfer, after you got your ready. Remember, first thing you have to do is get your ready word back, ready status word back from the device. You get a ready status word back from the device, then you can pass the byte. And you just keep doing this byte, byte, byte until you're all done, return to user. Just like I said, huh? I'm not making this stuff up. You probably thought I was making this up, didn't you? Didn't get that in your earlier class. Now, this is what's happening. Okay, any questions on programmed I/O? What's the downside to programmed I/O?
Yeah, OS has to manage all the IO devices.
The
OS has to-
processor.
Yeah. The CPU has to manage everything.
Yeah, CPU is doing all this work. It's sending the status word out, it's waiting for the status word to come back.
She used to get clocks on.
Yeah. And if it's waiting on the device, everybody in the computer is waiting on that device. The upside is it's pretty simple, right? Is it hard to write bad code this way? Well, okay. Relatively speaking, is it hard to? It's just a few lines of code. It would probably be really challenging to make this work incorrectly, right?
We
Yeah.
have people who they can do that here.
We
Yeah.
do. I give you that. That's why I said relatively. Yes, we can still mess this up, but it's pretty simple. But it takes a lot of CPU overhead, wasted cycles. So we were driven, of course, to improve. And that's when the interrupt-driven I/O technique came about. We started taking a look at, we've got this interrupt thing, this wonderful thing called an interrupt. And if we were to use it to help us build efficiencies in I/O transfers, what would that look like? And this was the form that we used for many years once we started using interrupts as part of the I/O mechanism. Okay, so the way this looks then is that I have, in this case here, I have the need to issue the status word and wait until it's ready, is the response. And then I can start transferring my data, right? But notice here that the first thing I did is I enabled interrupts. And then after I did that, I called the scheduler. Let's see what that's all about. Let's see what that's about. Okay, because over here is where I'm actually doing the transfer, yeah? So what's going to happen here is that your interrupts are always in play in an interrupt-driven system. However, I will put this up. Really? Not all interrupts are equal. As a matter of fact, we have levels of interrupts. Typical interrupt design usually has like 0 to 15, sometimes more, very seldom less. And what these means is that when you're, what this means is that I can design different interrupts that have different priority levels, right? So some interrupts might be a little bit more important than other interrupts. Let's say, for example, a page fault. A page fault is probably a little bit more important than, say, an I/O device saying, I just finished transferring a byte of data. Think so? Yeah, I think so. Same with the CPU fault. Kind of up there in priorities, okay? Yeah, it would like that. Yeah, that is like the one that's up here. Yeah. So 0 is the highest priority in our interrupt system. Going down to the larger numbers, which are lower priorities. That's why I drew it 0 high, 15 low, sort of, memory aid. So what happens is that your CPU will always be in a different level. And you can change levels. And what we mean by that is I can set my interrupt level to, say, 7. And what, if I set my interrupt level to 7, what that tells the CPU and the entire motherboard and the daughter boards, the whole system, is that I will recognize and accept interrupts 0, 1, 2, 3, 4, 5, 6, 7. But these are just going to have to wait. I will temporarily ignore these if I've set my interrupt level to 7. Okay, because what this allows us to do is it says, some interrupts can wait, meaning I can finish this job and get on to the next process, right? If I can finish this little bit of this job and then I restore my interrupt level so I can then fully process interrupts, this enables us to still continue to make progress on our work while recognizing that some interrupts I just can't ignore. And depending upon what it is you're doing, you'll set this to different levels. Typically, you'll never go lower than 7, except for some cases when you are actually doing some systems work down here. But that's very common. So what we're doing here, when we say enable interrupts, what we're really doing is we're saying, let's accept all interrupts, or let's accept interrupts up to 12, or whatever that particular scheme happens to be. Okay, so in this scheme here, I enable interrupts, I set it to 15, so everybody can interrupt me. I want my I/O device to interrupt me. I may want to have one of my other sibling processes interrupt me. Okay, it's saying things like that by setting them all the way up to 15. Every interrupt can interrupt me because I want to know when this I/O device is done. Right? That's why I want to enable interrupts. And then I go ahead and I do work. Right? I turn on my printer because I want to talk to the printers. I wait till I get my ready, and then I go ahead and initiate. In this case here, I initiate a register with the initial byte, and then after I've initialized it with the initial byte, I called scheduler, which said, okay, go ahead and put me into ready blocked, right? That allows another process to then go from ready to
Run state.
ready in memory to
Execution cycle?
Run state.
Zombie? No.
Run,
Only a few
run,
minutes.
run.
it starts with an R. No, ready in memory to
Run. Run.
run. Oh man, we're supposed to remember this stuff, right? Run. So I have a process in the run state. It enabled interrupts. It got the I/O device. Then it called scheduler, which meant it transferred itself out to blocks in memory. And the process that was at the head of the what?
Ready.
But the process that was at the head of the what?
Queue.
What queue?
The ready queue.
Ready queue. The process that was at the head of the ready queue then gets to go in and run. That's what that says. It's pseudo-common. All right, so we did that. Another process is running. This process is waiting for byte transfers. When the interrupt is raised, tense. When the interrupt is raised, then the process that's currently in the run state gets to transfer to its kernel mode, right? And it processes that interrupt handler, which says, oh, go move these bytes, which it will do. Notify the process that was waiting for these bytes over here, although it could be in what other state?
It could be blocked, or it could be, swap.
Swap.
Could it be in zombie too?
No,
No.
because the only place you can go from zombie is where?
Run. Yeah,
No,
there
you
you go.
can't go back.
No, no.
This is a one-way street.
Wait, so are those considered memory leaks then? I mean, are they just like running or like what are they doing? I mean,
Zombies?
obviously they're not running, but.
Zombies definitely can create memory leaks. A different kind of memory leak. Usually when we talk about memory leaks, we're talking about in-process memory leaks, but
Right.
yeah, you could definitely lose system memory this way.
Yeah.
And we used to have that problem until we did a better job of this.
Compilers got errors or something like that.
One.
No, it's actually
Like
the,
a firmware issue or?
no, it's actually the system software itself that's managing the memory space for the zombie processes.
Gotcha.
So where can the zombie go?
Well, hopefully out of memory, hopefully just like it's destroyed.
Non-existent?
Yeah.
Yeah.
Heavily dead or something.
Yeah.
Yeah.
So the process is running, transfers the stuff, and then it tells the process that's in one of these two states here that was waiting for that data, that data is available, it's ready, and it can then transfer to ready in blocked or ready in memory and go back to its thing, right? With data now. In the meantime, other processes were running the CPU. It wasn't hanging around just waiting for somebody, right? Pretty cool. Questions? Interrupt driven? We've got some more to talk about with interrupt driven, but does that make sense? What's going on there? Okay. We also talked about how to map the data with the process that's waiting for it, right? Wasn't that chapter 2?
Believe so.
I believe so.
Yeah, we talked about that. So that's the other thing, is when the process that is running gets that data from the I/O device, because it went over to kernel mode, right? There was a queue. Remember, there was a queue in each. This is what we were talking about, which data construct, which data structure construct we were talking about. Remember? Uh, yeah, yeah.
I'm not sure, referring to.
There was one particular data structure we introduced, right? And it had entry points based upon the state. There's a data was in, huh? Monitors, exactly. Remember monitors? They're fantastic because they're doing exactly what we want to do here. Is when this I/O device for that process generates data, we want to tag it out of its own queue and then put it into, oops, I made the main system, they all go here, right? So that when that process runs, it knows where in the queue to go get its data, because that I/O device, between when that process started the I/O transfer and then that process runs again, that I/O device may have been called by 15 other processes in the meantime. So you've got to queue all of those all that data, different data transfers, so that the right process gets its right chunk of data. So that's going on when we're doing all this. See how this is all starting to come together? This is the most fun class we teach in the computer science program.
Yay.
Everything comes together here in this class. Okay. Any more questions about interrupt driven? See what we're doing with this? Seeing how it works? You can draw this out for your turtle. Hamster, cat, dog, whatever. I don't know. Living friend. Okay, so now let's go talk about DMA then, or DMA controller. Okay, so remember, this is the one that has the little CPU in there, a little older technology, but it still works, right? So here's what's going to happen. Because the downside, oh, I'm sorry, we forgot to summarize the downsides and upsides. Before we go back to DMA, interrupt-driven I/O. What's the downside to interrupt-driven I/O? Is that? kernel user space is being used, and the kernel user space is being used to still do all of the byte-by-byte transfers. We have freed it up, plus side, we have freed it up so that it is no longer blocked waiting for every I/O. We can transfer the CPU to another process now. We fixed that problem. But we still have the problem that, okay, when that device is ready, the CPU itself is still transferring all of those bytes. Okay, so that's the main plus, main takeaway from this approach. So to solve that, we want to use this little CPU. Except we won't call it a CPU because that'll confuse everybody, right? This little processor. So the CPU with the DMA controller will do the following. When it's ready to do an I/O operation, it will contact the DMA controller and say, I want you to transfer either an address, a starting address for where to move bytes into, or the starting address of where to move bytes out from. So this is the address of where bytes are going into or coming out of. It's also going to transfer the number of bytes to be transferred. And then it's also going to give it the control word. Okay, this is the word and this is the signal that you're looking for to turn on this device and that it's acknowledged that it's ready. Okay, this is what it looks like. So that's what control is all about. The CPU gives all that to the DMA controller. The DMA controller then takes over that transfer operation. The CPU, in the meantime, if your code is not written such that it's blocked waiting for that transfer, if you write your code so that you have other things you can go off and do after you initiate the transfer, then your code will continue to work and do other stuff, whatever you had coded it up to do. So you could tell the DMA controller, go get this stuff, and I'm going to go do this other work until you tell me this work is done. I say that very deliberately because a lot of times up to this point, when you're given these assignments, these class assignments and stuff, you're worried about doing a very specific serialized task. Your program will do this, then this, then this, then this, and then you're done. But most of the times in the real world, you have a bunch of things that you are doing all in parallel with each other, and sometimes you just need to initiate I/O operations. You don't need to stop and wait for that I/O transfer. As a matter of fact, you want to do that the least amount of times. You want to go ahead and do other work. Sometimes you have to wait. Sometimes that thread needs to wait until that I/O transfer was complete. Great, you put your work in other threads. Okay? But even that thread, we want to optimize. So if an I/O transfer can be started, and that thread can go off and do other work, and when the I/O is complete, then go to a function to process that return value, it's even better. So that's the whole purpose of DMA controllers. Understanding this architecture enables you to write code that runs more efficiently. Okay? So it initiates the DMA controller. DMA controller takes over all the I/O transfer at this point. CPU is free to go off and do other things if the programmer is smart enough to do that. What the DMA controller then is to talk to the device. This example, here's the disk controller, saying, I want you, and it's waiting for the ready status word. When it gets the ready status word back, it checks the act with the return value, make sure that's correct for the control word that it was given. And at that point, the DMA controller will then initiate the data transfer from either from main memory to the disk controller, or from the disk controller to main memory, depending upon whether it's a read or write. When it is completed that operation, the DMA controller then will issue an interrupt to the process. An interrupt, all interrupts go to the processor. It will raise an interrupt. The CPU will say, that's interrupt 11. That's from the DMA controller. And then it knows to check the status word back from the DMA controller, say it was a good transfer or a bad transfer, and it can then decide to go do other things, whatever it is you programmed it to do.